our second contribution, we welcome Dr. Amir Abramovich, researcher and lecturer at the Electrical Engineering and Electronics Department of Ariel University Center of Samaria, Israel. Dr. Abramovich is expert in the field of development and characterization of detectors and focal plane arrays for the terahertz band, as well of quasi-optic design of terahertz band components. Please.
Thank you very much. Okay. Good morning to all. My name is Amir Abramovich, and thank you for the introduction. And I would like to thank the organizers and Ariel for inviting me to talk about quasi-optical design and focal plane arrays of terahertz millimeter wave imaging systems. I will start with the layout of my talk. I will give a short introduction. I will discuss design parameters, imaging ability of focusing elements, quasi-optical design approaches for imaging systems, description of a specific system that we are developing in our lab, and I will demonstrate some DSP and super resolution that we did in our imaging system. Okay. First, I would like to define what is an image. Imaging can be considered as measuring the radiation from different directions and arriving from different directions. Imaging, as you know, is an approximation of the reality. And quasi-optics deals with the case where the size of the aperture are small compared to the size of the wavelengths. There are several configurations for imaging. I will start with the scanning imaging system. Here you can see a scanning mirror that make the beam of, in our case, Gaussian beam. I will discuss it later. Scan the object and collect the object by one pixel, and it can be a receiver, and we obtain an image of the object plane. Another imaging configuration is using a focal plane array. This configuration is the configuration that we use in our lab. In this case, we have an imaging mirror, which can image the object on the focal plane array, and the focal plane array collects the image and can present it on the computer screen or any imager. Another kind of imaging is interferometric. In this case, we measure the Fourier image. In this case, we measure the phase difference between 2 points. So for each point, we need 2 detectors. And after collecting the points, or the Fourier points, we can inverse Fourier transform them and obtain the image. We have 2 kinds of imaging. We have the passive and we have the active imaging. Each of them has its own properties. I will go over them very quickly because most of you are familiar with them. Well, in the passive, we know that all natural objects emit radiation in the passive millimeter region and terahertz. It is not invasive. It requires very sensitive and expensive detector, as we heard in the previous talk. Usually, it's based on the scanning because the technology is not mature enough. It's limited in the dynamic range of the values measured, and it's mainly based on diffused from the surface. In active imaging, it requires illumination source in order to illuminate the object. Simpler detection instrument is required. We can work with lower SNR, and it can be direct detection or heterodyne detection. It has a large dynamic range, and it's based on specular reflections from the object. The advantage of millimeter and terahertz is well known to you, but of course the penetration depth compared to IR and visual, millimeter wavelengths offer better angular resolution than microwave, and we can trace gases by remote sensing, since the interaction between terahertz and millimeter wave and materials, gases in this case, is very unique, and the absorption lines can be detected, and according to them, we can recognize traces of gases or materials. It's not only for gases. Design parameters. Well, the most important parameter is the sensitivity. It was discussed in the last talk, but we can see that for passive systems, the minimum detectable temperature is NT over square of B tau. And an example is if we take NT of 3000 Kelvin and bandwidth of 3 gigahertz and the constant time of tau of 10 milliseconds, we can obtain the 0.5 Kelvin that it was discussed in the last talk. In the active systems, we are talking about the delta P minimum that RMS that can be detected, and it depends on the temperature or the noise temperature of the detector and the bandwidth. Now let's discuss design of focal plane arrays. An ideal imaging system would image a point source in the object plane to a point source in the image plane. But in the reality, the things not like this because of the nature of the wave. And we have an extension of the point and it become blur. The blur can be is given by B diffraction, and in our case, if we take the main ring, the main bright ring, which contain about 85% of the radiation of the point source, we can calculate its dimensions. In the case of our system that I will present later, we are working on 100 gigahertz, and our F number is 2, and we can find that the diffraction blur is about 7.5 millimeters. One more important thing, the trend to decrease the size of the elements or the pixels of the focal plane array must consider or take into account this constraint put by nature of the physical of the wave and the apertures of the imaging system. Everyone knows that Nyquist theorem tell us that we need about 2 samples per, or twice, we need twice samples compared to the required distance. So if we would like to be with to be compatible with Nyquist, we have to design our focal plane array within the distance of delta x, which is half of the blur of the diffraction. Field of view is important for outdoor and even indoor imaging. It's mainly determined by the camera sensor, but in case of a scanning system, it depends on the ability of the scanner to scan with the angle while keeping good quality of the beam. Because if you go to larger angles, you may suffer from imperfections of the Gaussian beam and geometrical optics, as I will discuss later on. Focusing systems. Well, we need, in our case, three main things. We need antenna gain, beam size, and beam quality, as I mentioned. There are difficulties. We need focal plane arrays of about 10 by 4 pixels. We requires the system, the aperture dimension, we would like them to be small, but we're constrained by the wavelengths and the diffraction requirements. We would like to decrease the blockage of the system, because if we are working, for example, with on-axis mirrors, the blockage is a major factor. And we constrain to work in very small f numbers because of the limitation of the aperture and the limitation of the wavelengths. Okay, now I would like to discuss some methods and approaches how to design a quasi-optical system. Well, the old method of geometrical optics is, of course, can help us. The geometrical optics is based on conservation of energy. It's based on Snell's laws, and of course the principle of least time by Fermi. Ray tracing is a very good tool when we are working in the visual and IR, because we are working with large f numbers. When we would like to work with smaller f numbers in the order of 1, we have to work with thick lenses, and geometrical aberrations will increase. We have some problems with the geometrical optics method. A better description of millimeter waves and terahertz can be done with Gaussian beam. Well, Gaussian beam, as you know, is a solution of the paraxial wave equation. And if we solve this equation with the Gaussian solution, we can receive the electrical field distribution of the Gaussian beam, which is given in this equation. And as you can see, is a function of R and Z, where omega is the beam spot, and R is the curvature of the wavefront of the Gaussian beam. Phi 0 is the phase shift of Gaussian beam. Okay. We mentioned that Gaussian beam can imitate quite good the propagation and millimeter and terahertz imaging systems and quasi-optical system, but it we have to take into account two things. One is the beam truncation, and the second is losses, and the phase shift that can be caused by the interaction with the boundary of the quasi-optical components. A better method is the ABC matrix with the Q parameter, with the Gaussian beam parameter Q. Gaussian parameter beam Q is obtained when we derive the electrical distribution of the Gaussian beam, and it can be written in this formulation. And the big advantage of this parameter Q is that it can be used in the ABCD matrix of geometrical optical components. So we can use all geometrical optical methods with the Q parameter of the Gaussian beam, where the parameter Q, we can, knowing parameter Q, we can calculate omega and R of the Gaussian, of the electrical Gaussian beam, and it's a great aid to the quasi-optical analysis. The hybrid approach is a matter of fact combination of several methods. It's said, according to this approach, we use Gaussian beam for the propagation to the optical elements. We will use ray tracing through the optical components and a single diffraction calculation, propagation to the far field or to any other required plane that the designer would like to check. I will go now over some optical components, not deeply, but I would like to mention the lens, that if we are using the principle of minimum of least time, we can find that the surface is hyperbola when n is larger than 1, and this is the case. We can see it here. And as we all know, there are many commercial spherical lenses, and we can see here that commercial spherical lenses can be as good as hyperbolic when we are operating in a paraxial limit. In small angles, the curves of a sphere and parabola that we will discuss later and hyperbola are very close to each other, and they can be used. And the reason is obvious, because to produce a spherical, for example, spherical plano lens is much cheaper and simpler from the industrial point of view. If we would like to check now refractive focusing with mirrors, using the principle of least light, we will find that parabola is the ideal surface for focusing and paraxial beam or collimated beam coming to the parabola. And we can show that as can be shown here, if a parallel beam enter the surface of a parabola, it will converge to the focal point. now there is a big issue that I will discuss later, is whether to use a reflective design or reflective quasi-optic or refractive quasi-optics. Well, if we are using on-axis mirrors, the problem of blockage is very big, and it is not so not so good for solution. A better solution is to use off-axis parabolic mirror, but also with parabolic also with off-axis mirrors, we have a certain problem which I will mention. Mirrors has the property of freedom of absorption, can handle high power. They are the performance is enhanced by the aperture and the parabolic or ellipsoid. But, as I told you, there are several problems, which include the skin depth and distortion and cross-polarization, as I will discuss now. Skin depth is depend on the kind of the metal, and we can see that for the cases of metals lower than skin depth, some radiated beam that will enter the surface of a metal will radiate to the other direction, and part of it will be reflected. So it will cause to a losses. In this table, we have some numbers of metals and materials at 1 terahertz. Here we have an example of aluminum, and know that for unpolarized light, we have we can the metal or the surface reflects about more than 90% of the incident beam on the metal. For the polarized light, it depends on the polarization. It can be it is different, as it can be seen in this example. Off-axis goes to distortion. The distortion caused due to the difference the difference in the wavefront of the Gaussian beam due to the curved component. And as we can see here, for a 90-degree off-axis mirror, we have a distorted Gaussian beam as shown in this graph. Another example is when you need to focus a beam and you would like to focus it equally on the image plane. You will find that due to the off-axis, the beam spot in each position of the image plane is different. As you can see here, it's magnification of this image. Of course, that such phenomena goes to the decrease of the image quality. And if the off-axis is big, it can damage the whole image. There is a cross-polarization, which goes to change of polarization of the beam, and it can decrease the beam quality, as well as surface accuracy. If the surface is not, for example, polished well, the beam will be diffused from the mirror, and of course it will damage the focal point or other instrument. It depends what its application. Now, after we go over all this stuff, I would like to suggest a method of designing a quasi-optical system according to the steps shown in this block diagram. As we can see in this block diagram, at the beginning of the process, we have to decide what quasi-optical components and what system architecture we would like to employ for a specific project or application. After this, we have to consider the beam waist radius and the beam waist location, which is very important parameters for the quasi-optical design. And then we will have the quasi-optical configuration, which I will explain later. After this, the beam truncation and beam coupling and frequency dependence will be considered. And then evaluation and optimization will be demonstrated. And if the system not achieve its goals, we may have some iteration between the two and return to the quasi-optical configuration. We'll try to change and to get the required performance of the image of the quasi-optical system. Well, the beginning, we have to decide about the architecture and components. Basic architecture quasi-optical components are commonly mirrors, lenses, polarizers, frequency-sensitive surface, diffraction grating, Fabry-Perot interferometers, resonators, feed-ons, and more. Here we have some examples of frequency-selective applications. Here we can see a high-pass surface. Here we can see band pass. Here we can see band stop, and here we can see another band pass. It's an example of components that we may use in our design. Another very interesting application is the use of resonators. In this case, it's a resonator that can measure the attenuation of gas filled inside a cell. This is the Fabry-Perot. Here is the antenna. Its incident beam enters this beam splitter. One arm go to the focal plane array, to the Fabry-Perot interferometers mirrors, while other is measured by the second antenna, where when the gas is filled with any aerosols or gas, the change in the obtained frequency can be measured, and the gas inside can be characterized. So this is an example of a Fabry-Perot interferometer. Now, the second stage, we have to decide about the beam waist radius. Beam waist is a property of the Gaussian beam, and there are several kinds of components, and the importance of the size of the beam, it's different from component to component. I would like to show you an example of a Fabry-Perot interferometer. As you can see in this table, the components are in order from the no critical, highly critical, and a determined component. For example, feed horn determines the waste of a system, as we all know. But here you can see a Fabry-Perot interferometer which is filled with the electric material. And we can see that it is moderate critical, and we can see here that the same Fabry-Perot interferometer filled with air is highly critical. Well, the difference is evolved from the diffraction inside the Fabry-Perot. When using an dielectric Fabry-Perot interferometer, the diffraction parameter is given by this formula. And we can see that when we are using a dielectric, the diffraction parameter is decreased. This makes the system less sensitive to the size of the waste. In contrary to the air-filled Fabry-Perot interferometer, in which the diffraction parameter will be higher. So, as we can see, the determination of the beam waste is an important parameter while designing a new quasi-optical system. All those components and their properties has to be taken into account. The location of the beam waste is another important parameter because mostly it influenced by the frequency. If you are working in one frequency, the focus of a lens will be in this position, for example, and in another frequency, it will be in another position. So the quality of the system, if it's wideband, can be significantly different into even close frequency. What can be done? Well, using the matrix method and the quasi-optical parameter Q, we can find the ABCD elements of the matrix for the case of thin lens. For example, we will take the thin lens as an example, and we will use the Q out parameter of this lens, including distance D in and D out in the input and in the output of the thin lens. Now substitute the ABCD parameters in this equation. We will obtain Q out, and from Q out, as I showed you before, we can have D out and omega O out, omega 0 out of the Gaussian beam. Of course, we impose that the Q will be imaginary in order to have the waste, because where Q is imaginary, is pure imaginary, it means that R is going to infinity, and it's the beam waste. From this formula, we can see that there is only one position in which the distance of the focal point is not depend on the operating frequency, and this distance is when D in is equal to F. In this case, D in is equal to D out, and does not depend on the frequency. In other frequency, we can see here the parameter ZC, which is the confocal range, and it's a frequency dependent. It is very analogous to the case in geometrical optics. When you put a point source, a distance 2f from a lens, and in this case, you will receive a point source in the other side of the lens in the same distance. A question raised why there is a difference between the quasi-optical parameter Q and the optical geometrics, the optic geometrics. The answer is that the difference in the phase shift in Gaussian beam, it depends on Z. So it changes along the propagation of the beam, while in the geometrical optics, it is not the case. This is the reason to these changes in the differences between the operating with Gaussian beams and optical geometric. Now we have to decide of the configuration, and one of the major questions that we have to deal with is whether to use a refractive or reflective optic or quasi-optics. We will discuss this in a moment. And of course, the performance and the operating of the feed horns, which are usually the input for the quasi-optical system. It is very important to couple most of their energy or radiation into the fundamental Gaussian mode. And here you can see the performance of several kinds of feed horns, and you can see it's something wrong with the slide that it was changed the perspectivity, but this is the dimension of the waist to the size of the horn aperture, and this is the amount of coupling from the energy in the energy coupled to the fundamental Gaussian mode. And you can see that there are certain ratio between the waist and the aperture of the antenna that can provide very high coupling of the energy to the fundamental Gaussian beam. Now we will discuss beam truncation. As you know, beam truncation decreases the energy in the beam due to the truncation of the beam, because it's a physical truncation. It's an aperture or an optical component that truncate part of the beam. So one problem is decrease of power. In addition, there are two more factors that we have to take under consideration. One of them is reduction in the original omega zero of a system. In this case, if a truncation is done, the beam will be broadened much more than it was originally designed. You can see here some examples for an untruncated beam, 50% truncated beam, and 25% truncated beam, and see the broadening of the far field pattern of the beam. It's very significant, and it should be taken into account while deciding about truncation or apertures of a quasi-optical system. Another factor is increasing the side lobes of the far field pattern. In case of truncation of the beam, the side lobes of the Gaussian beam will be increased on the expense of the main lobe, of course. Now we have to take all the considerations and to optimize a system. The first step is to employ the ABC matrix with Q. It is effective to start with a waste produced by a coupling device, which is usually the input of the system, as I showed you 2 slides ago, previous slide. This is the input of the system. And now, using the ABCD method to check the output, which can be any plane that the designer decide. It is, of course, not complete, because ABCD method, as I told you, doesn't take into account all the factors involved in the designing of a quasi-optical system. There are more parameters that should be considered. For example, the loss, polarization behavior and frequency response, which does not take into account in the ABCD method. And for the case of imaging, and it's very important, you have to check the diffraction from the imaging component or from the last component to the focal plane array. As I will demonstrate in later in this talk. Now I would like to show you some applications of the methods that I discussed with you until now. Those systems was designed and built by our labs in the last, I think, about 10 years, more or less. And I would like to start with a 4-axis parabolic mirror arrangement that was used for a very accurate spectrometer. Here we can see the off-axis parabolic mirror, 90-degree parabolic mirror. The design is such that it compensates the distortion and the cross-polarization of a single off-axis component. You see, it's come in couples. And as you can see, now, without influence of diffraction, we start with a point source, and we end with the point source. Another configuration, in order to decrease the dimension, is to use off-axis mirrors with 15 degrees. In this case, again, a focal point is obtained about here in the middle between the two off-axis parabolic mirror. You can put a unit or sample in this position and check its spectroscopic response to input to different frequency input from here to here. Again, note to we start with a point and we end with a point. This is a very interesting system in which we can perform 2 measurements, reflection and transmission, one after the other without changing the sample position, which is very important for spectroscopy. We can see, by the way, it's a point source with hemispherical mirror that was mentioned in the last talk. We simulated this hemispherical lens here, and the power, the signal incident on the off-axis parabolic, the first off-axis parabolic mirrors, which you can see, and maybe I save a question. You can see that the focus point is not on the sample. And you ask yourself, it should be on the sample, isn't it? It should be. But remember, this is geometrical optic rays. It is not the Gaussian beam. And as I told you, the Gaussian beam and geometrical optic rays are not have the same focal point, as I mentioned in my previous example. So thus, the focal point is not exactly on the sample. And in this case, we use the Gaussian beam simulation rather than geometrical optic simulation. So this is the reason. And it's very important to consider this issue. Here we can see the high resolution spectrometer that we have in our lab in order to check interaction between materials and W band radiation. This is all electronics to control the beam and the frequency of the radiation, but we have here two parabolic mirrors that produce a more or less collimated beam, not 100%, of course, as we saw previously, but in this case, the sample interact with the beam, not with the focal point, which is very important if you would like to design an imaging system, because in imaging system, and especially in an active imaging system, you have to illuminate the whole object, as here. And the property of the object and the interaction with the, in this case, millimeter wave or other frequency band is very important information. Here we can see some results of this spectrometer. It's polyethylene, POMC, and PMMA, which are all industrial plastics. Polyethylene is used very widely in the millimeter wave and the terahertz band. Here you can see the samples, which are about 100 millimeter over 100 millimeter size in order to be larger than the beam spot, because small sample will give bad results, because part of the beam will go directly to the mirror without going through the sample. Another configuration is the reflection one. Again, off-axis parabolic mirror, diagonal mirror that direct the beam to the sample, which located under absorbing material. Beam reflected from the sample to the second diagonal mirror, to the off-axis mirror, and to the detector. Very efficient design of reflection measurement. And I want to show you here a measurement that we made in our lab. We took a sand and we took a water, and we measured the specular, of course, reflection from them. By the way, this is a specular reflection measurement. diffused measure is not in the beamline, so it's diffused, but not to the mirror, and anyway, it's not directed to the detector. But in the case of the sand of water, we can see here the reflectance of sand and water. We can see that water is a little bit more reflective than sand in W band spectroscopy. This is the focal plane array that we designed for our imaging system. I showed you an example in one of the previous slides that we found that the diffraction limited size is about 7.5 millimeter. It was one of the previous slides. And here you can see our detector, which is based on a glow discharge detector. It's a new method that we develop in our lab. And here you can see 8/8 focal plane array for W band radiation. Each pixel looks like this neon lamp, which you are all familiar from everyday life. Each GDD has its own reflector that direct the beam directly to the midsection of the neon lamp, which is the interaction region, which is the responsivity is best between the two electrodes of the lamp. So it's a special parabolic reflector. And here you can see a photo of one of those parabolic reflectors. Those holes are used for the lamp ports here. Yeah. Okay. This is our scanner, 2 multiplied by 36 pixels. Also is operating in our lab, and we can take photo, images in the W band region. It's a moving. We can move it, and it's computer controlled. Now, this is the setup that I showed you before. And in this setup, we have a source. We have an off-axis parabolic mirror in order to collimate the beam. And using a diagonal mirror, we radiate here a sample or an object. It is better to put the object horizontally because we can move it and locate it very easily. It's located under absorption material, of course, and the reflection from the object return back to the diagonal mirror and to the imaging mirror, which is 500 millimeter, and the image mirror image the object on the focal plane array, for example, the 8/8 or the 3 multiplied by 36. This is a simulation results which can show very accurately the influence of each of the factors. Simulation can separate the influence of geometrical aberration and diffraction. This is the object. This is the image. The image is inverse because of the optics. Here you can see the geometrical aberration of the image, only geometrical. Those geometrical aberrations are due to the very small off-axis position of the imaging mirror, smaller than 10 degrees. But when you are looking at the diffraction limited, at the diffraction simulation, we can see that the image the object becomes very blurry due to the diffraction. This is a photo of the experimental setup. Here you can see the 500 millimeters mirrors. Here is the off-axis parabolic mirrors used for the illumination of the object. And in this case, this is the object over a sand. It's a metal F shape which is located on a sand. All of this is located on absorbing material. This is the diagonal mirror that I mentioned in the diagram. And those are the results. We can see here that the F shape is very obvious in the image that we obtained in this case using the GDD focal plane array. Also, when we use a plastic over sand, the image was detected by the system, as you can see in these two images. Post-processing of the image is required in those cases. And I would like to demonstrate the super resolution process that we used in our lab. Here you can see a very small metal piece. It's about 15 millimeters. When we are using the original photo without, or raw data, as we call it, using the 8/8 focal plane array, this is what we obtain. But now, if we are using very basic super resolution method that moves the focal plane array 4 times in the horizontal direction and 4 times in the vertical direction, we can obtain a 32/32 image. In this case, the object become much more improved compared to this. And if on this we add some simple DSP algorithms, we can have the object seen very well and can be detected and recognized almost without any problem. And another example that we made, we took an L-shaped metal, even smaller than the previous one, and we repeat this process. And you can see here just that something is here. And after super resolution, L-shape is apparent. And after DSP, it is no doubt that this is an L-shape. Okay. Okay, I would like to thank you. And